Hello and welcome to this video. In this video, we have to take a quick look of chapter number 3 of university physics. Chapter number 3 of university physics, which is motion in 2 or 3D, 3 dimension. So up till now, we have discussed motion in 1D. So for any point in space, you need only one coordinate to specify the position of the particle. Now, if we are in 2 or 3D, so you need to specify, for example, this point, you need to specify 3 coordinates, x, y, and z, x, y, and z. So every point in space, you need to specify, 3 coordinates. And the line joining from the origin to that point is your position vector r. Okay, this is your position vector r. Either you can go along x, can go along y, and along z. So you along x, you have the unit vector I. Along y, you have unit vector j. Along z, you have unit vector k. So the position vector can be written in terms of its components. So this position vector, which is r, can be written in terms of its position vector components. So it has 3 components now: xi plus yj plus zk. So there are 2 ways to reach the point P, either directly along this line, or you can go along x, y, and z to reach the point P. Now, because now the position changes, for example, if the particle is at this point, we suppose that this is your point P1, and particle changes its position and it goes from P1 to your P2. Now it's become, this is your 1, 1, and 1, your P2 coordinates x2, y2, and z2. So it changes its position. So this will become your vector 1, and now this vector will become your r2, and this is the change in position. And we can add these vectors by using the head to tail rule. This is your vector. So the change in position, which is your position vector or displacement vector, in 3D displacement vector, like what we did in 1D, we have only x, which is x2 minus x1, but now we have del r. This is your del r, which is nothing but r2 minus r1. So this is change in displacement. Now, what is the average velocity now? The average velocity is the displacement divided by the time interval between the 2 points. So your v average is defined as the time rate of change of displacement, which is nothing but r2 minus r1, t2 minus t1. Same as the in the 1D, we have x2 minus x1, t2 minus t1. So the direction of this vector, so direction of the velocity, is the same, so have the same direction as this displacement. So they have the same direction. So both have the same direction. same direction. So velocity is having the same direction as displacement. So in this case we have this direction. Okay, so now what's your instantaneous velocity in that case? So instantaneous velocity is the rate of change of position vector with respect to time at any given instant. So your instantaneous velocity is the rate of change of position vector at any instant of time. So this v is limit del t 0 del r divided by del t, which is nothing but dr by dt. So dr by dt is your instantaneous velocity, is just nothing but the first derivative of the position vector. So the direction of v at any instant is the tangent to the path, Okay, so we can get the speed just by taking the magnitude of velocity vector. Okay, so your speed is just the magnitude of your velocity vector. So now your velocity is vector, it depends upon r, and this velocity has components along x, along y, and along z. So your velocity is defined as dr by dt, and your r is defined as xi, yj, zk. So what's your velocity vector now? So along x, along y, so this is dx over dt I, dy by dt j, dz by dt k. So this is your velocity. So this component, which is vx, this component is your vy, and this component is your vz. So v vector is vxi, vyj, and vzk. So velocity has x component, y component, and z component. Okay, so the speed, because the speed is a particle moving in xy plane, okay, xy plane, particle motion is in xy plane, so it has vx component, it has vy component, this is your vy, this is your v vector, and this is the angle alpha they are making. So the speed, which is nothing but the velocity vector, is vx squared, vy squared. This is your speed. And the direction is nothing but the tangent alpha, which is vx over vy over vx. So this is your direction. The direction of the instantaneous velocity is given by this angle. alpha. Now we learned that the velocity, now we're moving towards the acceleration. So acceleration is describe how the velocity of the particle changes. Acceleration is how velocity changes. Changes in velocity, magnitude, which is speed, direction, or both. Okay, so the average acceleration vector, so average acceleration vector is defined as the rate of change of velocity vector, which is nothing but the v2 minus v1, t2 minus t1, and this direction, and the direction of this average acceleration is the same as the velocity vector del v. Okay, del v. So the direction is the same of the velocity. So your average acceleration is nothing but the time rate of change of velocity vector. Similarly, we can find instantaneous acceleration. So instantaneous acceleration vector, because we are in 3D vector, is the instantaneous rate of change of velocity with respect to time, or it is defined as A is the limiting case, limit delta t tends to 0, del v over del t is nothing but dv dt. And we know that your v vector is nothing but vxi, vyj, and vzk. So your acceleration, which is the instantaneous acceleration, is d by dt vxi, dvy over dt j, and dvz over dt k. So this is your axi, ayj, and azk. So this is your acceleration vector. So this is the acceleration along x, this is the acceleration along y, and this is the acceleration along the z-axis. So in general, this acceleration has two components. So as the velocity changes, as the particle moves like this, at every moment in time it's changes its velocity. So this acceleration, if it's changes its direction, velocity is changes direction, so this acceleration has two components. One is perpendicular to the velocity. This is the velocity vector. So one is perpendicular to the velocity vector, which is the normal component of the acceleration, and one is which is along the velocity vector, which is your parallel component, or what we call the tangential component. And this is your normal component, which is perpendicular to the velocity vector. Okay, so the tangent to the path, which is parallel to the velocity, is changes speed only. That is no information about the direction. So this will give you about the change in speed only, change in speed. the perpendicular component, perpendicular to the tangent path, which is this component, tell you about the change in direction. So this component of the acceleration will tell you about the change in speed, and this component will give you the change in direction. So we have the parallel component, which is a cos of alpha, and this angle, this is your acceleration vector, okay, and this is your angle alpha. So a cos of alpha, and v perpendicular is a sine of alpha, and we can find alpha by this formula, cos of alpha, a dot v, a magnitude, v magnitude. It's just nothing but the dot product between a and v. So we can find the direction of this angle alpha with this formula. So the direction of the acceleration vector will depend upon, the direction of acceleration will depend upon the change in the velocity vector. So the direction of acceleration vector will depend upon the change in velocity vector. Okay. The direction of the acceleration vector is tangent to the path, and the particle moves in a straight line. Is just give you the information about the speed, and this will give you the change in the direction. So if the perpendicular component, this component, if this component is 0, then the particle is moving along a straight line. So if this component is 0, if a lambda is 0, then the particle is moving in straight line, because your velocity and acceleration vector both are in the same direction, moving in a straight line. Velocity and acceleration, a parallel, is the same direction. So this is the motion along a line case. Okay, so when the particle is moving with constant speed, and it's moving along a path, with a constant speed, or just like moving along a circular path, then its parallel component, which is, this is the velocity, parallel component of the acceleration is 0, and we have only the normal component of the velocity. So if the particle is moving with constant speed and moving in a circle, the parallel component is 0, but the perpendicular component is not 0, and this motion is known as circular motion. So if the particle moves with non-uniform speed, then both the parallel component of the acceleration and perpendicular component of the acceleration is not 0. It means the direction of the acceleration vector depends on whether the particle's speed is increasing or decreasing. So it depends upon whether the particle is increasing or decreasing speed. So because the speed is not uniform, it's changing. So when the object moves with non-uniform speed, its both components will not be 0. Then the motion is in non-uniform speed, and it can follow any kind of trajectory. Okay, now we're going to move on the important topic of this chapter, which is the projectile motion. So projectile motion is a two-dimensional motion. Is the motion of the particle or a projectile is a motion which is given by an initial velocity, which is given by some initial velocity, and then body falls under the action of gravity. So the projectile motion is that motion which is given by some initial velocity and the body fall under the action of the gravitational acceleration or gravity. Okay, in that ideal case we ignore air resistance. So the path followed by this projectile is known as its trajectory. So it will look like this. It's a 2D motion, it's a two-dimensional motion. It's happening in XY plane. If this is your origin and the particle is given some initial speed, so it follows a path and fall under the action of gravity, and this path is known as trajectory, and it's given by some initial velocity at certain angle, which is theta naught. Okay, and the acceleration is due to gravity, which is only along y, which is negative g, and your x is 0. Your acceleration along x is 0, but your acceleration along y is negative. So projectile motion is analyzed. Two motion is the horizontal motion with constant velocity and vertical motion with constant acceleration. So projectile motion analyze two motions. One is horizontal motion, which is with constant velocity, and vertical motion with constant acceleration. Okay, so when the projectile is and the particle which is projected at some angle is known as projectile, so I will use projectile. So when a particle moves in an xy plane and follows a path or a trajectory like the projectile, so it's given by some initial velocity. So at every moment in time it has some component of initial velocity along x and some component of initial velocity along y, and it's making an angle theta naught. And we know that what is the x component is v naught cos of theta naught, and v naught y, which is v naught sine of theta naught. Okay, so at every moment in time, over here it's velocity component along x, velocity component along y. This is a velocity vector. At the highest point, at the highest point, it stopped there, so its velocity vector, which is the y component, goes to 0. So the velocity y component goes to 0, and then it changes direction and then move like this. Okay, so at this point, this is the x component and this is your y component. Okay, this is your x component and this is your velocity vector. This is at this point, we like say that this point p1, this is velocity vector v1, this is the direction of your velocity vector v2, because vy is y component is 0, and this is v3, this is your v3x, v3y, and it falls under the action of gravity, because the motion along the x, which is along the x with the constant velocity, which means the acceleration along the x will always be 0, and your acceleration along the y will always be negative g. So now we're going to see the components of the velocity and the position. So for example, if you wanted to find the position from here to here, this is your r, this is your r naught position, this is your r. So we wanted to know that what is the position at any given time. So this position is given by this r naught plus v, this is the vector, v naught vector t plus 1/2 at squared. So the velocity at any instant of time is given by v naught plus at, and the x component of the acceleration is 0, but the y component is negative g, and g is 9.8 meter per second squared. Okay, so now we're going to see what is the motion along x direction and motion along y direction. So along x direction, its initial velocity is v naught of x, which is v naught cos of theta naught. Its acceleration along x is 0. Its velocity along x is constant, and its x equation becomes x equals to x naught plus v naught of xt. Now along the y, we have the initial component v naught of y, which is v naught sine of theta naught. Then your acceleration along the y is minus g, which is nothing but 9.8 meter per second, and vy equals to v naught of y minus gt, and the y equation will become y naught plus v naught of yt minus 1/2 gt squared, and the final velocity of along the y will be v naught squared minus 2 g del y. Del y means y minus y naught. Okay, so if we wanted to find the distance from that origin to that point, which is nothing but the magnitude of r which is nothing but x squared plus y squared. Because it's a 2D motion, it's happening in the plane. So this is your distance. So if we wanted to know what is the speed of the projectile, speed is nothing but the magnitude of the velocity, which is vx squared, vy squared, and the direction of the motion, which is tangent of alpha, which is nothing but vy over vx. So the projectile motion is the motion which is given by some initial velocity, and it falls under the action of gravity. The motion along the horizontal axis, along the x-axis, is with constant velocity, and vertical axis with constant acceleration. So acceleration along x is 0, acceleration along y is minus g. Okay, so your projectile can be thrown in various ways. For example, it can be thrown like this. Okay, it can be thrown like this, and it can be thrown like this as well. Okay, so it's v naught, it's v naught, v naught. So this is your angle theta naught. Here we don't have an angle theta naught. Here we go. So in that case, the angle is positive. In that case, your angle is 0 and 0 degree. And in that case, your theta is negative, which is below to the horizontal. Okay. So by solving the problem for the projectile, you need to have a strategy. So strategy for the projectile problem, you need to select your coordinate. You need to select your coordinate system first, from where the projectile motion is going to be started. So coordinate system, when you start your coordinate system here, then your x naught becomes 0, your y naught becomes 0. Then the next step is to resolve the initial velocity into x and y components. So what's your x component? Vx is v naught of x cos of theta naught, v naught of y sine of theta naught. This is your. Now you need to analyze, you need to analyze the motion along x and y. So what's your x equation? So x is x naught plus v naught t, because the motion along the axis is constant. And what's your y equation? So y is y naught plus v naught of y t minus 1/2 gt squared. And this is along x. So this is your x equation. Then this is your y equations. So when you find your x and y, you can find the distance from the origin, which is nothing but x squared plus y squared. Okay, and if you analyze the the motion, and you can find vx and vy, you can find the speed of the projectile, and you can find the tangent of alpha is nothing but vy over vx. Okay, so when we're going to solve the problem in the tutorial video, you will see we're going to apply this strategy for the projectile motion. First, we're going to resolve the coordinates. Then we resolve into the initial components of the velocity along x and y. Then we're going to analyze the motion of x and y, and then we can find the velocity, the distance from the origin, and the speed of the projectile at any moment in time. And in projectile, what we actually wanted to know is if the projectile is projected with some initial velocity, we wanted to know how far it go. Then we wanted to know how high it goes, and then we wanted to know how much time it takes from origin to get maximum distance. So this is how far it goes is your range projectile, how high is your height of the projectile, and it's this time of flight. So let's solve for these three values, what we wanted to know. So if we have a projectile in xy plane, we projected it with some initial velocity v0, it's making an angle theta along the x-axis, okay, and it follows and it falls under the action of gravity. So what we wanted to know, what is the maximum height it reaches, and how far it goes. So what we wanted to know, the maximum height, and maximum range. So we apply now the problem strategy. We now apply the problem strategy. We decide this coordinate system. This is our origin, and this is x0 equals to 0, y0 equals to 0. The acceleration along the x is 0. The acceleration along the y is minus g. Okay, so this is your theta naught. Okay, so this is our origin, and this is given. Okay, so when the projectile is symmetric in projection, so it moves with this and it follows under the action of gravity. So what we wanted to find, the maximum height and maximum range. Okay, so we are given by the, now we have decided the origin in this coordinate x0 0, y0 0. Now we decided the coordinate system. Now the velocity now resolve into velocity x and y. So what is the x component of the velocity is v0 of x, v0 cos theta naught, v0 of y, v0 sin theta naught. Okay, so when it reaches to the maximum value, maximum height. When it reaches to that point, we learn that at this point it has only the x component, so the y component will be 0. So this is our second point. First point is coordinate system, second point is resolved into the velocity. Now we're going to analyze the motion along the x and y, and at this point this vy goes to 0. It means vy goes to 0, and we wanted to know how high it goes. So it means we wanted to know the motion along y, so we wanted to know y. So we're going to write the y equation. So your y equation, in which we don't have time, so you don't have time, so we're going to write the y equation, which is v naught of y squared, v naught y squared minus 2g y minus y naught. Your y naught is 0, your vy is 0 as well, so you're left with 0 equals to v naught y squared minus 2g y, and this y is your height, how high it go along y. So this will become now vy square 2gh, because the velocity is y component is 0 at the maximum height. So h is now become v naught of y squared over 2g. So what's your v naught of y, which is the velocity, initial velocity component along the y, which is v naught sine of theta naught divided by 2g whole squared, and we have the height, the maximum height or the height of the projectile is v naught squared sine squared theta. So this is a generalized form of the height of the projectile. So what we wanted to know, the maximum height. So we have angle theta naught, so we have sine squared theta. So when sine theta naught goes to 0, its theta goes to 0, and when sine theta naught is maximum, which is 1, when theta is 90 degree. So when we substitute this theta equals to 90 degree, we will get the height maximum is v naught y squared, v naught squared divided by 2g. This is your maximum height. So now we wanted to find the maximum distance it traveled. It's along x, so we need to analyze the x equation. So your x equation is nothing but x equals to x naught plus v naught of xt. So your this maximum distance will become your range. This is 0, and we left with v naught of xt. So because we don't have time, so we need to eliminate this time as well. So for projectile motion, when you wanted to calculate time, every time use this equation, y equation. So y is equals to y naught, y is equals to y naught plus v naught of y t plus 1/2 ayt squared. So this is your y equation. Okay, so when we're going to reach at that point, okay, which means its velocity going to be 0, so your y goes to 0 as well at this point. Okay, so this y goes to 0, this y naught is 0. Your velocity along y goes to 0. Because this velocity will not going to 0. So this, or just before that point, so your v naught y t minus 1/2 ay is minus g is 0. So your vy t naught of t is 1/2 gt squared. So when we divide both side by t, so this t will be cancelled out, and you get t, which is nothing but 2v naught y divided by g. So we're going to substitute this t over here, and we, over here, and we get our range, which is v naught of x to v naught of y over g. So v naught of x, we have v naught cos theta naught 2, and v naught of y, we have v naught sin theta naught divided by g. So r will become v naught square cos 2 cos theta naught sin theta naught divided by g, and this 2 sin theta naught cos theta naught is nothing but sine 2 theta. So your range formula will become v naught square sine 2 theta naught divided by g. So your general expression for the range. So how do we find the maximum range? When this will become 1. So when it will become 1, when we have theta is equals to 45. So we get the maximum range when v naught square sine 2 multiplied by 45 degree, and we have divided by g, this will become 90, and this range is maximum is v naught square over g. So maximum range is v naught square over g, and it will be at the angle theta 45. So we apply the same problem strategy to solving this problem. We design a coordinate system, then we express our velocity along x, along y, then we analyze the motion along the x and y, and find the maximum height and maximum range of the projectile, which making a certain angle with the origin. Okay, discuss the circular motion and relative motion. So when an object moves along a circular path, okay, so its velocity vector at every moment in time changes. Okay, so its velocity vector changes every moment in time. It covers the distance along a curved path, and it moves along a circular path with the constant speed. Then this motion is known as a circular motion, or with uniform circular motion, which means this is moving with the constant velocity. And we learned earlier, when it moves along the constant speed, it has the only component of the acceleration which is along the radial direction, which is your perpendicular component. This is your velocity vector and this is your acceleration vector. So it's only the perpendicular component which is directed toward the center of a circle. Okay, so this acceleration is known as the instantaneous acceleration or the centripetal acceleration. So this instantaneous acceleration always points towards the center, toward the center of a circle. Okay, and this acceleration is known as the centripetal acceleration. Okay, so along the curve path, when the object at point P1 changes to point P2, okay, so we wanted to calculate the magnitude of this centripetal acceleration. So it changes its position along the path. So this is the change. So this is the velocity at P1. This is your velocity at P2. Okay, and this is the center of a circle O. This is the radius of a circle R. This is the radius of a circle R. And this is your change in position from point P1 to P2. So if we see this making a triangle, and if we further extend this, so this thing is equivalent to this thing. So this making a triangle, one, this, and this is making a triangle, and this thing is making a triangle. Because of my drawing is not good, so these two triangles are equal. So there is a theorem in mathematics that says that the ratio of the corresponding sides of a similar triangle are equal. So the ratios of corresponding sides of similar triangles are equal. So del V over V1, so this is your del V over V1 is equals to del S over R. So we define our average acceleration. Average acceleration is nothing but the change in velocity divided by time, and we take the magnitude. So we can substitute delta V vector from here. So we get V1 over R. We will take this V1 over here, V1 over R del S by del T. So we define this acceleration as instantaneous acceleration. Okay, so this become an instantaneous acceleration when del T tends to 0 and it converges to a point. So this becomes a velocity as well, or it converges to that point P. Okay, so this is your velocity V1 and this is your V1. So your instantaneous acceleration will become V1 square over R, or your centripetal acceleration, which is nothing but V1 square over R, or V square over R for general velocity. Okay, and this acceleration is also known as the radial acceleration, which is V square over R. Okay, so when the object moves along a circular path having constant radius and moving along the circle with the constant speed, it has only component of the acceleration, which is perpendicular component, and this acceleration component is known as the radial component, the centripetal acceleration, and instantaneous acceleration. The same thing, which is have three different names. Okay, this is v square over r. So now if the object is moved from here and I complete a circle, the time required to complete a circle is known as the time period, the time for one revolution. So this time is defined by the velocity. If you define like velocity is nothing but del s over del t, and this del t is the time from this complete a one revolution is your time period. So time period is nothing but del s over v. What's your del s? Starting from here, covering from here, we cover 2 pi r, small r, which is v, where r is the radius of a circle, this r. Okay, so this t is your time period to complete one revolution is 2 pi r over v. This is the radius of a circle, and this is the velocity of the particle. So we can find the velocity if we know the time period, which is nothing but 2 pi r t. So your centripetal acceleration or your radial acceleration will become v square over r, and your v is 2 pi r divided by r. It's your square. So 4 pi square r square divided by r, and this has t as well. So let me correct it. 2 pi r divided by the capital T whole squared, and we left with 4 pi square r square divided by t squared r. This one r will be cancelled out, and your radial acceleration will become 4 pi r over t square. So if you know the time period, you can find the radial acceleration as well. So if the object is not moving with the uniform speed, like what we are in a roller coaster, we are always speeding up and speeding down, so the speed is not uniform. So when we have non-uniform circular motion, so if the speed is not uniform, then we have a non-uniform circular motion, like what we have in a roller coaster. It always speeding up and speeding down. It's moving like this. Okay, so when the object is moving in a roller coaster on with non-uniform speed, so the acceleration now has the velocity is changing in that direction. So acceleration has two components now. So this is your perpendicular component, which is along the v, which is this parallel component. Okay, so this is your radial component and this is your tangential component. So the radial component is the same, perpendicular component, which is radial component, is v square over r, and then the tangential component, which is the parallel component, which is nothing but the dv dt. Okay, the tangential acceleration component and is parallel to the instantaneous velocity, and it's parallel to this velocity vector. So these a parallel is parallel to v. Then our total acceleration is parallel perpendicular. This is the vector, and the magnitude of this acceleration is nothing but a parallel square, a perpendicular square, or we can write as a tangential square, a radial square. And we can find the direction alpha between the vectors, okay, between the vectors alpha, okay, which is nothing but a radial divided by a tangential. So when the speed of the object is not uniform, it's moving along the circular path, then this motion is non-uniform circular motion, is example of roller coaster. Then this motion has two components. One is the normal component or the radial component, and one is the tangential component, which is parallel to the velocity vector. And we can find the total acceleration vector is by summing the parallel and perpendicular component, and we can get the magnitude and direction of the acceleration vector. Now we're going to discuss the relative motion. Now the relative motion or relative velocity. So for example, you are in a train, and this train is traveling, with 3 meters per second speed, and passenger walks inside the train with a speed of 1 meter per second, with a speed of 1 meter per second. So what is the passenger velocity? It looks like it's a very simple question, but it has no single answer. So it's look like a simple question. What is the question? What is the passenger velocity? And there is no single answer to it. There is no single answer. Why? Because who is observing the motion is important. Okay, so according to you, you are sitting on a train, the same train. According to you, this passenger P is moving with 1 meter per second velocity, because you are moving also with 3 meters per second. But if a person standing outside the train, and this is at rest as well, it's not moving, according to this person, which is at A, okay, so at A, this person is moving in this direction, because it's moving 3 meter per second and 1 meter per second. So according to this person, its velocity is 4 meter per second. So now we have to specify which observer we mean, and we speak of the velocity relative to that particular observer. So we have to keep in mind the particular observer. The walking passenger's velocity relative to the train is 1 meter per second. Her velocity relative to this person outside the train is 4 meter per second, and it's according as or with respect to you is 1 meter per second. So each observer equipped in principle with a meter stick or stopwatch form what we call the frame of reference. Thus, a frame of reference is a coordinate system plus the time scale. Okay, so now we're going to define this. Let's use this symbol A for a person outside, P for the passenger, and use the B for the frame of reference of moving train. Okay, so the train is moving along a straight line at a point P relative to the frame A. So the position of a passenger with respect to A is this, and the position of P of passenger relative to B is X P B, and the position of the origin of B with respect to A or A B, which is BA. So the position of A, so we can show that that this position is the sum of two positions. In other words, the coordinate of P relative to A is equals to the coordinates of P relative plus the coordinates of B plus the coordinates of B with respect to A. Now the x velocity of P relative to frame A is denoted by VPA, which is nothing but the time derivative of this. So this is dx PA divided by dt, dx PB divided by dt plus dx BA dt, or we can write VPA is equals to VPB plus VBA. So if the frame of reference of A is measuring the velocity of this passenger, which is moving with 3 meter per second in a train, and he is moving with 1 meter per second. So this is moving 1 meter per second plus the train is moving to the observer with 3 meter per second. So the velocity of the object or the passenger with respect to A, which is the person outside the train, is 4 meter per second. So this is the Galilean transformation transformation of velocity. So this is in 1D, and we can generalize it to 3D, and then it will become like a velocity vector, because then it has 3D. So this is classical mechanics. So we are having velocity very less than c. So this Galilean transformation or Galilean relativity valid in that case. But when we move comparable to the speed of light, then this transformation does not hold, and we need a special relativity, which is the Einstein theory of relativity, and Einstein revolutionized our theory. So up till now, so we can add velocity according to the specific observer who is observing the motion according to this Galilean transformation law.